Do you remember back in elementary school when your science teacher told you that atoms were the smallest things in the universe? And then you got to high school and your science teacher told you that was all a lie, because atoms are actually made up of smaller things called protons and neutrons and electrons, and these were actually the smallest things in the universe. Well, it turns out that was kind of a lie too, and everything you know about the atom is wrong, or at least partly wrong. In this video, we're going to learn about chemistry on its tiniest scale. I'm Aidan Dawson, and this is the science of small. Let's look at this glass of water. Just like everything around us, we know it's made of matter. But what does that mean? Let's zoom in. We can see that the matter is made up of molecules, two hydrogen atoms bonded to one oxygen atom, giving water its identity. Though we're not done yet. We know that there's more to this glass of H2O. If we zoom in even farther, we see electrons orbiting the atom's nucleus. This nucleus is made up of protons and neutrons, nothing we haven't seen before. But let's venture deeper still. Here we are, in nature's fundamental world, the chemistry of the atom. We can't get any smaller than this. What you're seeing would have been unheard of even 60 years ago. Here, the building blocks that make up the entire universe are finally given the spotlight. As you may have guessed, there's more than one type of fundamental particle, or elementary particles as some like to say. So just like the periodic table of elements, we have a table of our own. As you can see, there are a lot less fundamental particles than our own elements. We're going to cover up some of these particles for the sake of getting a better understanding as to what they are. But by the end of this video, you'll have learned about them all. Let's head back to that water example. We're looking back at the nucleus of the atom. Here, it's revealed that protons and neutrons are actually made out of something even smaller. 3 things to be exact. 3 of the same type of fundamental particle, quarks.
But hold on. If the proton and neutron are both made up of quarks, what makes them different? Well, it turns out that the protons and neutrons are made up of 2 different types of quarks. Believe it or not, the actual scientific term for this is different flavors of quarks. These 2 types of quarks are the up quark and the down quark. The only difference between the 2 is that an up quark has a charge of plus 2/3, whereas the down quark has a charge of minus 1/3 and is a little bit heavier. Whoa, fractional charges? Those both look and sound complicated. But in reality, it makes so much more sense if you look at it in this way. A proton is made up of 2 up quarks and 1 down quark. If we add up the charges, that's 2/3 plus 2/3 minus 1/3. This gives us an overall charge of plus 1. This makes sense because a proton has a positive charge. Now, if we look at a neutron, we can see that it's made up of 2 down quarks and 1 up quark. And if we add those together, negative 1/3 minus 1/3 plus 2/3, this makes the neutron have an overall charge of 0. It's neutral. The very identity of every element in the universe is determined by the number of protons in their nucleus, and these quarks are in charge of that. As you may have guessed, too, the amount of protons and neutrons in the nucleus also determines the element's atomic mass, which means the quarks are in charge of that as well. It's remarkable how these tiny, tiny particles can affect the world at a macroscopic scale, just like some of our labs in class. When performing our calcium carbonate using hydrochloric acid, you may want to know how many moles are in, say, 2 grams of the calcium carbonate. You'll use molar mass for this calculation, which is fully owed to the mass of the calcium carbonate, which is due to the quarks. The bigger particles that these quarks make up, like neutrons and protons, are called hadrons. Now, where have we heard that name before? At the Large Hadron Collider in Switzerland. Here, hadrons are accelerated just under the speed of light before they smash into each other. It's in particle accelerators like these where we synthesize new elements. Using large atomic nuclei, like that of titanium and berkelium, we send them flying down large tubes through the use of magnets. Just like what we studied in chemical reactions, the activation energy needs to be reached in order for the nuclei to get close enough together to fuse. Similar to our work with reactants turning into products found in the reaction rate unit, without the proper activation energy, the synthesis of new elements is impossible. But after all this talk about protons and neutrons, where does the electron come into all of this? Well, it turns out that the electron is a fundamental particle itself. Although it orbits around protons and neutrons, it is actually more like a quark in that sense. Unlike quarks, however, the electron has a charge of -1. This explains why we say it's negatively charged. Aside from that, the electron is much lighter than the quarks. In fact, it is over 9 times less massive than a single down quark. This is why when we talk about the atomic mass of an element, the electron's additive mass is usually negligible. You may be wondering, if the nucleus determines the atom's identity, then why are electrons important? Well, it turns out that every chemical reaction you've ever heard of, synthesis, combustion, halogenation, polymerization, every single one of them would be impossible without the electron. If there's one fundamental particle that you're going to care about in this grade 12 curriculum, it should be the electron. All the reactions we saw during our enthalpy, organic chemistry, reaction rates, and equilibrium units happen solely because electrons from one atom or molecule create ionic or molecular bonds with another atom or molecule. Electrons allow atoms to form bonds with one another. Without them, we wouldn't have any molecules. No molecular products, no reactants, no intermediates. For us, this comes directly into play when we look at certain chain propagating and chain initiating steps of certain reactions, like ozone depletion through the use of Freon 12. The reaction results in a free radical. What this means is that this atom has a certain number of unpaired electrons. Now here's where the electrons really become important. Other atoms take advantage of this unfilled valence shell by readily bonding to it. Here, the oxygen free radical is bonded with a chlorine atom, forming chlorine oxide. Indeed, this tiny fundamental particle truly affects our world at large in ways we can quantify and see in our classroom. Now, it's no mistake that the up quark, down quark, and electron are all arranged into one column on our table. These 3 fundamental particles make up all the matter in our universe. The chair you're sitting on, the screen you're watching this on, the air you're breathing in right now is made from up quarks, down quarks, and electrons. Now let's expand our horizons just a little bit. I'm going to reveal the quark's bigger brothers. Here, we see the charm, strange, top, and bottom quark, and they're more alike than different. Just like the up quark, the charm and top quark have a charge of +2/3, and just like the down quark, the strange and bottom quarks have a charge of -1/3, and just like the up and down quarks, they each have a pair that they like to join with. The differences between the quarks are mass. From left to right, the quarks get heavier and heavier still. So a charm quark shares all the same properties as an up quark, but it has more mass. The same goes for the top quark, but even more mass. This rule applies to the down, strange, and bottom quark as well. However, you'll remember that I said only the up quark, down quark, and electron make up our matter. So why is it that we don't see any charm, strange, or top-bottom quark combinations? To find out, I spoke to Mr. Cummins at Saunders Secondary School.
You basically have high energy and it condenses into mass, and some of it's stable and some of it's not. So the up and down quarks, very, very stable in the proton and the neutron in the nucleus. But the other ones are considerably higher energy, and they don't exist in that state for 25 zeros after the decimal point. So they don't last as long. They're too high energy. They go down to a lower energy state and give off another particle and become up and down quarks, pretty much.
If we think about Einstein's famous equation E equals mc squared, he's saying that mass could be equivalent to energy. Let's look at an example. With a quark that has a lot of mass, like the top quark, its equivalent energy is too great to remain stable. It is not at equilibrium with the space around it. In order to reach this equilibrium, The particle must decay, causing the energy to be released, though that energy manifests itself in the form of a bottom quark and another smaller particle. That's E equals mc squared at work again. What's interesting is that the newly formed bottom quark too is not at equilibrium with space yet. It's still too heavy. The energy is released again, manifesting itself into many smaller particles. This short-lived bottom quark serves as an intermediate in this fundamental reaction. Just like in this equation we looked at in class, the fluorine free radical is produced from the initial reaction, but only exists momentarily as the reaction proceeds, producing its final product. Think of that bottom quark as the free radical. It's created momentarily, but doesn't show up at the end of the reaction because it's too unstable. Isn't it extraordinary when macroscopic chemistry can be applied to the intensely microscopic world? Now that we've gone over the quark's bigger brothers, surely the electrons have siblings of their own. This is the muon and the tau. They're just fancy words for heavier electrons. They share all of the electrons' properties, like the charge of -1, but they have more mass, with the tau being the heaviest. Just like what Mr. Cummins said earlier, the muons and taus are simply too massive to be stable. And just like what we talked about earlier with the top quark, the muon and tau are not at equilibrium with the space around them. They release their mass in the form of energy in order to reach equilibrium. And this energy often turns into an electron and another small particle called a neutrino. When a decaying particle like a muon transforms into a smaller particle like an electron, it releases more than enough energy for this transformation. This extra energy manifests itself into neutrinos. Neutrinos are super tiny particles that don't have a charge, hence the name neutrino, like neutral. They move at just under the speed of light and have an incredibly small amount of mass, less than a millionth of an electron. Because of this, trillions of neutrinos originating from the sun and supernovas pass through your body every second without you even noticing. They're so unaffected by matter that they can travel through light years of lead with ease. Par for the course, there are 3 flavors of neutrinos. We have the electron neutrino, the muon neutrino, and the tau neutrino. The reason they have prefixes like electron, muon, and tau is because, for example, when an electron is created, an electron neutrino is created too. And when a tau is created, a tau neutrino is created as well. This is how we differentiate the 3. Although they barely have any mass at all, each neutrino from left to right is just a little more massive than the neutrino that comes before. The electron neutrino is the least massive, and the tau neutrino is the most massive. Along with electrons, muons, and taus, neutrinos make up the category of leptons. Here we are. We've covered over half our table by now, so let's recap. We have our 6 quarks, the top row having a charge of plus 2/3, and the bottom row having a charge of minus 1/3. We have our leptons, which are electrons, muons, and taus, which have a charge of -1, and their corresponding neutrinos, which have a neutral charge of 0. And remember, these 3 particles, the up quark, down quark, and electron, are the things that make all of our matter. Now here's where things get interesting. The next 4 fundamental particles deal with the 4 fundamental forces of the universe. These particles are called bosons. The 4 forces are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Every interaction that anything in the universe has with anything else occurs through these forces and the particles that mediate these forces. First up, the force of gravity. Unfortunately, we haven't actually found the particle that's responsible for gravity, but we'll know it when we see it. Indeed, the prediction of this graviton, as we like to call, is like previously undiscovered elements. When Mendeleev created his periodic table, he could follow the pattern of elements and their masses in order to predict as of then undiscovered elements and their properties. We know from experiments with gravity that the graviton must be massless, have no charge, and moves at the speed of light. Thankfully, since the force of gravity is so intensely small at the atomic scale, this video doesn't lose much by its omission. Next up is the gluon, and just like the name suggests, it kind of acts as a glue for the atomic nucleus. Gluons govern the strong nuclear force and are exchanged between quarks in order for the protons and neutrons to stay together, forming the atom's nucleus. The strong force is, as you may have guessed, the strongest force in the universe, which is why so much energy is released when an atom is broken apart. Now, why should us grade 12 students care about the gluon and the strong force? Well, chemistry is the study of matter and its interactions, and the mere existence of protons, neutrons, and the nuclei they make up is due to the strong force holding it all together through the use of gluon particles flying back and forth between the quarks. As you know, we kind of need elements for chemistry as we know it to exist. Now that we've touched on the strong nuclear force, let's look at the weak nuclear force. And spoiler alert, it's very, very weak. It only works on tiny, tiny distances. The weak force is in charge of particle decay. Remember earlier how that top quark decayed into a bottom quark to regain energetic equilibrium with space? Well, it's done through the weak force. As above, the weak force operates using force-carrying particles too. This time, there are two of them. The W boson, which can have a positive or negative charge, and the Z boson, which always has a charge of 0. It's neutral. It's easy to comprehend the W and Z bosons if we look at an example. For this, we'll need a neutron and an electron neutrino. Remember, neutrons are made up of 2 down quarks and 1 up quark, and the neutrino has an overall charge of 0. When the electron neutrino gets super close to the neutron, and I mean super close, like 0.1% the diameter of a proton, the weak force goes into effect. A positively charged W boson travels from the electron neutrino to one of the neutron's down quarks. The positively charged W boson turns the down quark into a positive up quark. Now that we have 2 up quarks and 1 down quark, we've just seen the weak force decay a neutron into a proton. But the process of losing the positive W boson makes the previously neutral electron neutrino turn negative. It's now an electron. Back to the original neutron. If it were to be inside of, say, a carbon-14 atom when it came in contact with the positive W boson, when it decays into a proton, the atom's identity is now nitrogen-14. This is because we added another proton to the nucleus. In our enthalpy unit, we learn about nuclear reactions that make the sun shine. In our sun, protons also decay into neutrons, and the energy given off by that atomic shift donates to the collective energy that the sun uses to produce light. All that energy comes from a nuclear reaction called the proton-proton chain. This involves protons becoming a neutron, making a hydrogen nucleus, then a helium-3 nucleus, then a helium-4 nucleus. As you can see, this forms many intermediates, though they're not as we know them, because they aren't molecular intermediates, but rather atomic nuclei. This nuclear reaction benefits from the weak force's harvested energy, and it allows the sun to give off heat for us on Earth. In conclusion, the weak force handles particle decay, which gives us energy, like from our sun. Finally, we have the electromagnetic force, which also works through a particle, something you may have heard of called a photon. A photon is simply a super tiny packet of energy. It has no mass, no electric charge, and moves at the speed of light because, well, it is light. A key way to think about a photon is that whenever you hear somebody say that something produces energy, they usually mean it produces a whole bunch of photons. Our enthalpy unit centered around heat of reactions and the energy that reactions produce. And you guessed it, all that heat energy comes in the form of photons. Photons make up our visible spectrum. The difference between each color is the wavelength of the photon. Red has a large wavelength and low energy, and purple has a smaller wavelength and higher energy. However, there are wavelengths that are outside our visible spectrum that our human eyes just can't see. Infrared light has a bigger wavelength than red light, but we just can't see it. What's interesting about infrared light is that we perceive this energy as heat. We can identify an exothermic reaction that happens in a beaker because the glass becomes hot to the touch. This is the result of infrared photons being released from the reactants as they become products. The chemical energy is given off as photons. Although we can't see these photons, we can feel them as heat. The full electromagnetic spectrum extends far beyond our visible spectrum, including radio waves, microwaves, infrared waves, ultraviolet waves, X-rays, and gamma rays. From left to right, energy increases and wavelength decreases. You can see how this energy increases by looking at the Freon-12 reaction from our reaction rate unit. The UV light has so much energy that it can actually break the bond to produce a free radical. This initiates the reaction. When photons have enough energy to break bonds, it is called ionizing radiation. Thankfully, our atmosphere blocks most of these wavelengths from hurting our bodies. As we learned in our reaction rate unit, one of the factors that increase the rate of reaction is heat. Oftentimes, we may put a beaker over a hot plate. That hot plate radiates infrared waves. But how do those photons translate to an increase in reaction? To find out, I talked to Mr. Cummins.
This is a kind of an involved question, but I think we can get to a quick answer somehow. You have to wonder how the photon's interacting with the material that's getting hot. When the photon's traveling, it travels as a wave as well, which is an electromagnetic wave. And an electromagnetic wave oscillate back and forth 90 degrees. And so every time you move an electric field, you move whatever's being affected by that. It's like an electric field, like a gravitational field. If I have something affected by gravity, like a massive object, it will move and create kinetic energy like a ball dropping. Same with an electrically charged thing. It'll oscillate and move in the electric field.
Now we know how photons are integral to our description of energy and how they affect our enthalpy and rate of reaction units. So these are the bosons: the gluon that glues quarks and nuclei together, the W and Z bosons, which are in charge of particle decay, and the photon, which makes up light and heat energy. Now that we've finally unveiled all of our fundamental particles, let's try to combine as many as we can inside of a description of an atom in a reaction. For the purpose of this example, let's imagine a single strange quark out in space. We know that they're quite massive and not at equilibrium with the space around them, so it releases its mass as energy, some of which turns into an up quark. Now, by chance, this up quark comes in contact with two down quarks, and the gluons pull them all together to form a neutron. Nearby, a muon neutrino comes whizzing very close to the neutron. The muon neutrino releases a positive Z boson, which makes one of the neutron's down quarks turn into a positive up quark. Now that we have two up quarks and one down quark, this hadron is no longer a neutron, it's a proton. However, since the muon neutrino lost its positive charge, it is now simply a negatively charged muon. But since muons are quite massive, it releases some of its energy to regain equilibrium, and some of the energy makes a new, stable electron. Now back to the newly formed proton. Let's imagine it happens to find an electron that, as we know, orbits the proton. We have hydrogen. Now let's say this hydrogen atom meets another hydrogen atom. The electrons allow the atoms to form a covalent bond. We now have H2. Now if I were to put this molecule in a tank of oxygen gas, nothing would happen. In order for a reaction to occur, we need to reach activation energy. So we apply some heat. This heat energy, as we said, is comprised of photons in the infrared spectrum. And boom. Using all the types of fundamental particles, we explained how on that one day in class the llama scared us all by making water very explosively. The point of this video was to put forward a better understanding as to how some of the things in our curriculum work. Rather than remembering that adding energy to a system increases reaction rate, you now know specifically how the molecules interact with photons in such a way that it increases their kinetic motion. We also saw how we could apply macroscopic concepts like equilibrium to the microscopic scale, like tiny things such as quarks or leptons. Ultimately, I hope that this video instilled a greater appreciation for the chemistry that we encounter on a daily basis, and that you learned sometimes in order to see the bigger picture, you have to get small.